Hi everyone, welcome to our lecture on acids and bases today. We'll be going over the Bronsted and Lewis acid and base definition, pKa, as well as understanding how the structure of an organic molecule affects its basicity, and then going over what inductive effects are. So just to give a really brief overview of organic acids and bases, this slide is basically going to touch on anything that you would need to know for this video. Just know that there's a lot of components to acids and bases, but these are the most high yield information to know. So here we have Bronsted acids and Bronsted bases, and you know there's multiple definitions of acids and bases. But the Bronsted definition states that a Bronsted acid is a proton donor, meaning it donates a hydrogen or an H+, and the Bronsted base is a proton acceptor, so it accepts the H+. Then we have the Lewis base and Lewis acid definition. So a Lewis acid is an electron pair acceptor, whereas a Lewis base is an electron pair donor. And I'm just going to really circle this definition here because this is the major definition that we'll be emphasizing today. So if we were to look at this reaction here, you would see that this hydrogen gets, this HCl molecule gets deprotonated, meaning that its hydrogen gets, I guess in a way, disattached from the chlorine here. And then it becomes a hydronium ion here, or H3O+, and here we have the Cl- that has lost its hydrogen. So as you know, we have acids, bases, conjugate acids, and conjugate bases. So here we have the acid reacting with the base. And the reason I know this is an acid has to do with the Bronsted definition. I know an acid is a proton donor, and a base is a proton acceptor. And when you have an acid that loses its proton, you get, as a result, something called a conjugate base, which I'm going to abbreviate with a CB here. And when you have a base that accepts a proton, you get something called a conjugate acid. Okay, so these are reactions that you should kind of understand what the conjugates are versus what the non-conjugates are, and how you get from a base to a conjugate acid, and from an acid to a conjugate base. Okay, and another important term to know is the Ka, which is the acid ionization constant. So it basically takes the whatever's in the products and puts it over the reactants. So here we have in the products the hydronium ion and the chlorine ion over the HCl, which is an acid. And water usually is not included in this just because it's a liquid, it's not really aqueous. And we only include aqueous things in this equation usually. So water is something you can leave out, but this is the most important thing, products over reactants. pKa is the negative log of this value, so just know that the lower the pKa value, the more or the stronger the acidity is. So something with very high acidity will have a very low pKa. And just know that K equilibrium, which is whatever direction that it tends to favor, will favor the weaker acid-base pair because this tends to be more stable. Okay, so these are just really quick bullet points to summarize organic acids and bases, but definitely review this material more in depth. This is just kind of an overview of basic concepts. So we're going to really go into detail about structure and basicity today because this is really important in organic chemistry particularly. So with basicity, it really has to do with how well the molecule is able to accommodate the electrons that it has and the electron pairs. So we're really going to look at the electron pair accommodation of a conjugate base. And so something that's really helpful to ask yourself when you're doing problems in acids and bases, from the base's perspective, the base it will ask itself, do I want to keep or give away my electrons? And there are certain factors that we'll go over in a later slide that affect whether or not the base wants to keep or give away its electrons. And this is in reference to the definition of a Lewis base, which, as you remember, is an electron pair donor. Okay, so let's take a look at this molecule here. We have here the acid, and here we have its conjugate base. So if we were to deprotonate this molecule here, we would get this molecule. Okay? And so when you have something that can better accommodate electrons, this indicates a stronger acid. And the reason for this is because this conjugate base can better accommodate its electrons due to certain factors such as resonance. And as a result, the rule is that when you have a stronger conjugate base, you have a weaker acid. And if you have a stronger acid, then you have a weaker conjugate base. That's just kind of the fact that they're opposites and inverses of each other. Similarly, when you have a better electron pair accommodation in a base, this indicates a weaker base. And the reason for this is because if you have a base that can really hold on to its electrons very well, that means that it doesn't really want to let them go. It doesn't really want to donate or give them away because it can accommodate them. It's comfortable in its home. So that's how I remember that when you have a base with a really, really good electron pair accommodation, this leads to a weaker base. So here again we have an acid, here we have its conjugate base. So between these two, if you were to kind of look at this, you would see that something like this has good electron pair accommodation in its conjugate base, meaning that this is a stronger acid. Okay, so this is just to kind of summarize the relationships between electron pair accommodations and the bases versus electron pair accommodations and conjugate bases. So recognize that these are different. Okay? So basicity can be affected by certain factors. We're going to talk about resonance as the first factor, and this leads to decreased basicity usually. And this is the number one factor that we should consider first when you're considering how basic a molecule is. So let's take a look at this structure here. This molecule, as you can tell, has resonance with these shared pi electrons here. In these oxygens. And the reason that resonance decreases basicity, there's two of them. The first is, of course, better electron pair accommodation. So if you remember in resonance, these electrons are delocalized, so they're spread out over multiple molecules or multiple atoms. So they're really comfortable. They're not really repelling as much as they would be if they were like squished together in a really confined space. So a molecule with resonance can better accommodate these electrons, meaning that now the space doesn't really want to donate its electrons anymore. And so this means that it has less basicity. Another reason that resonance can reduce basicity has to do with disfavoring processes that can cause loss of resonance. So, for example, you have these molecules over here at the bottom. So if you were to protonate this and form this carboxylic acid here, you have this loss of resonance. You have resonance here, now you no longer have this resonance due to that hydrogen being there. And this is disfavored, and then this actually leads to reduced basicity of the molecule, because now it doesn't want to donate its electrons as much, and it doesn't really want to accept protons either, because that means that it would lose its resonance. And similarly with this molecule, going from here to here, if you were to protonate this, this does not have resonance. So if you were to protonate this, it doesn't really affect it that much since it's not really losing any kind of resonance. And as a result, something like this would actually be a stronger base because it's better able to accept that proton, whereas this one would be a weaker base because it has resonance and it would lose it if it were to be protonated. And then sometimes resonance might not affect basicity at all. Usually it does, usually it reduces it, but just keep in mind that it's not an end-all be-all kind of statement. The next thing we should consider is atomic radius. And atomic radius, if it's very, very large, can lead to decreased basicity because you have a larger space and the electron density can be spread out over a larger area. So if we were to compare a fluoride ion and an iodide, you would see that, so here's the size of fluorine, for example. And since fluorine and iodine are in the same column in the periodic table, and atomic radius increases as you go down a period, or go down a column, a group, you would have a bigger atomic radius in iodine. And so, between these two molecules, iodine would have a larger atomic radius, meaning that more space in the atom allows for the electrons to be better accommodated. So this actually makes it a lot more stable than something like fluorine, where the electrons are very confined in the smaller space. So they want to get out. They want to be donated and form something like HF, which is an acid. Whereas this means that they are very able to be accommodated. These electrons are chilling in like this hotel, this paradise, very spacious for them. So they don't really want to leave as much. And so this means that it has reduced basicity here. So it's less likely to form something like HI because it doesn't want to donate electrons anywhere. The next thing we want to consider is electronegativity. So, and this is really electronegativity regarding the atom that donates the electrons. So for all of these, we're concerned with the atom that has the electrons that would be donated in an acid-base pair. So let's look at fluorine and nitrogen here. So the electronegativity is 4 here, and for nitrogen it would be 3. So between these two, fluorine, of course, is a lot more electronegative, meaning that it wants to pull its electrons towards itself. It doesn't want to really give them up. And so as a result of these electrons being really, really strongly pulled towards itself, it's less likely to donate these electrons to form an acid-base pair, as opposed to something like nitrogen, which is less electronegative, has a weaker grip on the electrons that surround it, and so it's less likely to form, or so it's more likely to donate its electrons than a fluorine is, and therefore form something like NH3+, which is its acid here, or conjugate acid here. So when you're considering things like radius and electronegativity, if you're looking at atoms and comparing that across a row, you want to consider electronegativity over atomic radius, just because, as we know, electronegativity tends to increase going across a period. And if you actually want to consider something going down a group, you'll consider the atomic radius. So as we know, the relationships in groups are that going down a group, you have a larger atomic radius. So we also want to consider inductive effects. And inductive effects is basically when you have electron withdrawal or donation through a chain of atoms. So key thing here is you have something like super electronegative, or something that's really, really electron donating somewhere down the line in the molecule, and it's affecting the electrons where the proton, or where the acid-base reaction is concerned. So let's take a look at something like this, which has a fluorine attached to it. As we know, fluorine is the most electronegative atom, so we would see that compared to something like methyl here, which is attached, and this is not very electronegative, so I'm just going to put like not as electronegative here. So when you have something like this, due to inductive effects, it's basically pulling electrons towards itself, and this in a way makes it very makes this bond in my mind, like it makes it kind of hard for this bond to remain strong. And so I kind of imagine it as this fluorine is a tight rope, kind of just pulling, doing this tug of war, pulling these electrons towards itself. Now this hydrogen can't be attached as strongly since these electrons are all moving away towards the fluorine. And so now this actually makes it easier for this hydrogen to be released from the molecule. And so when you have something with a highly electronegative atom, you tend to have a stronger acid because this hydrogen is really easily released. As a result, when you have a stronger acid, the rule is that you will have a weaker conjugate base since they are opposites and inverses of each other. Let's take a look at this molecule now. So compared to the fluorine here, we have a methyl group, which I said is not as electronegative. So you don't really have anything pulling the electrons as strongly towards the methyl group here. So this hydrogen is better able to stay attached to the rest of the molecule. So this is considered a stronger or weaker acid compared to this molecule up here. and as a result, it has a stronger conjugate base. And the reason it's a weaker acid is that it is less likely to give up its proton here, since there's not as much electronegativity pulling the electrons away from this bond. So in summary, something to consider with inductive effects is also the proximity of the electronegative atom to the source, to the proton that's being lost. So the closer your proton is to the source of the inductive effect, the stronger the strength of the effect. And then something else, the last thing we want to consider is formal charges. And so increased basicity can actually be caused by formal charges. So the reason for this is you have more electron repulsion. So if you remember, formal charges are usually due to having like excess electrons around. So here we have a hydroxide ion. And since there's so many electrons around itself, there's a lot of repulsion here. This means that it actually leads to a stronger base because these electrons want to be given away. It doesn't want to keep it as much because there's too much instability here. As opposed to something like water, which is a weaker base, as it does not have a formal charge and it does not have these excess electrons. So that's acids and bases. Thanks for listening.